I'm here to be the chair on behalf of Iran Sergey. It is my great honor to introduce you the tutorial speaker, Matthew Mirman. He's a PhD student from ETH Zurich, and his research focus on AI problems viewed as differential programming through programming language techniques. His research in specifically applying program analysis techniques to analyzing existing learner systems, and then use this as components in new learning systems. So Matthew can take over.
Hi, thanks for the introduction.
Your mic is not on.
I just put it on. Still? You can't hear me? Hello?
Yeah, we can hear you.
Okay, thank you. Hi, yes. Thanks for the introduction. So again, I'm Matthew Mirman. I'm a PhD student at ETH Zurich and the SRI lab. And generally, I've been working on trustworthy artificial intelligence and specifically verification and certification systems for neural networks. So today I'm going to be presenting a tutorial on formal methods and deep learning. And the first part of this tutorial is going to be focused on approximate certification methods. So before I begin, I'd like to note that this is a presentation of work that was published jointly with my advisor, Martin Vetchev, and numerous other professors, PhD students, postdocs, masters, and undergraduates at ETH. So now I think you guys have all noticed that deep learning is appearing everywhere. It's now pretty much ubiquitous as part of software engineering, and companies such as Google and Amazon are using it for self-driving cars and automated voice assistants. It's even being used for translation systems, which I use frequently, being in Zurich and not speaking very much German. And it's even appearing in healthcare systems. Now, healthcare systems and autonomous driving are the most striking of these applications, given that they're fairly high-risk scenarios. If something were to go wrong, if you were to misdiagnose somebody, or the self-driving car is to turn right in the middle of a street, there could be serious harm to the people involved. And this is highly non-desirable for companies or governments or anybody deploying AI systems. So what I've been focused on is ensuring that these systems, that we have formal guarantees and we can protect these systems and we know how they behave. And what we've noticed in the past few years, many researchers have discovered that neural networks do not necessarily behave the same way in production that they do in training time, and are even sometimes susceptible to what we call adversarial attacks. And these sorts of attacks, you're given a network that appears to be behaving correctly, and you give it an image that it classifies correctly. For example, a picture of a cat. It says this is a picture of a cat. And then in one type, you can perturb all of the pixels by an imperceptible amount or just a few pixels, such that you can't tell the difference. It still looks like the same picture of a cat to you, but now the neural network is saying it's a snake. And of course, because this is intentional adversarial manipulation, this presents a serious security risk in addition to presenting a flaw in how the model appears to be understanding its world. Many types of these attacks have been developed, and some of these attacks have even been created in the physical world. For example, in this ICML 2018 paper, the authors 3D printed a turtle and used this physical turtle, which looks like a turtle to you and to me, hopefully it looks like a turtle to you, and gave it to a neural network that was otherwise behaving correctly. And now the neural network classifies it with very high confidence to be a rifle. There are other examples in not just the image domain. Sorry, my computer is frozen. There are other examples in not just the image domain of adversarial attacks. We've seen adversarial attacks on audio systems where you can add an imperceptible amount of noise to audio, either leveraged physically in the background or as post-processing after the fact to get the audio classifier or transcriber to behave completely incorrectly. Given that there are these physical attacks which can manipulate neural networks into behaving how an attacker would want the neural networks to behave, many in the industry want systems that they can have guarantees about. And this doesn't end at just training the model and testing on a hidden subset of the data set that is used, that is collected originally. We might want to use formal guarantees about specific properties of a neural network, such as that the network behaves fairly in order to build these models. So the pipeline that we envision for building neural networks includes this trustworthiness in the building process, in addition to in the testing process. So what we see as the way that artificial intelligence systems are moving forward is that at first they will be trained specifically to satisfy guarantees in a provable way, and not just trained to satisfy a test set, which we know that they're attackable during. And then we want to test them and test such properties as robustness, fairness, and interpretability, and see if the models that we've trained actually do satisfy these properties. If the models that we've trained don't satisfy these properties, this isn't the end of the story for the model. We want to be able to debug models and figure out where the cause of the failure is in the model, and then repair the models. If the models are then now satisfy the guarantees that we want, we can finally deploy the model into a real world environment, such as in a self-driving car. But even then, it would be ideal if we could continually check that the models are behaving correctly. So there's this need for formal verification that arises here, because as it turns out, most of the properties that we would want to verify are over sets that are too large. And more importantly, if we have just empirical verification, we end up with a cat and mouse game. So there's been a lot of work on designing attacks and creating empirical defenses. But in these works, we don't have eternal guarantees about our model. Somebody can come around after we've created a defense and create a new attack that specifically targets this one defense. And this happens back and forth. And this is clearly not ideal from an industrial standpoint and presents significant liability. So our goal is to provide formal guarantees on trustworthiness to deep learning models, such that they're to minimize the liability involved. So the problem statement of neural network certification is that we're given a precondition over neural network inputs phi, a neural network, and a postcondition psi over the network outputs. The precondition can be considered a set of possible inputs, and the postcondition can be considered a set of allowable outputs for that set of possible inputs. This is, of course, a fairly simple certification statement, but it does cover a lot of scenarios that we see in practice. So here, what we want to be able to do is that we want to show that the neural network applied to every element of this set of preconditions is a possible element of a set of psi. If we cannot show this, if the property does not hold, we want to be able to find a counterexample I in phi such that the network does not satisfy psi. So building trustworthy models and verification systems presents a few dimensions that we're able to work in and that require separate focuses of research. The first is that different application areas have different constraints and needs, use different types of models. For example, the NLP domain frequently uses transformers, and the vision domain most commonly uses convolutional neural networks. Inside each of these applications, they have different needs. For example, wireless communications guarantee would be that the networks involved, the physical networks, never go down, whereas in the healthcare, you want to guarantee that misdiagnoses are not made. The types of specifications that we use in each of these applications thus changes significantly from cases like geometric specifications, where we're looking at physical changes to the image, and we also see specifications such as fairness specifications, where we want to make sure that a model does not change based on signals that we know a priori are unimportant. Another dimension that changes how we might approach building trustworthy AI systems is the types of architectures that are used. Most historic architectures are based on ReLU networks and essentially convolutional neural networks, but we're frequently seeing more residual networks and unusual or architectures with a more significant nonlinearities, such as transformer networks. And of course, the final, one of the most important dimensions here is the type of system that you would want to apply to get guarantees on your artificial intelligence systems. For example, we might want to use complete verification because finding counterexamples is important. So we would apply MILP or SNT techniques, or we could be using dual or convex relaxation and approximate methods to get trustworthy artificial intelligence systems, or we would possibly want to build systems with guarantees from the ground up, such as in abstract training methods. Then the last dimension that I want to discuss is the type of guarantees as a whole. These guarantees can be either deterministic, where given a specific input or set of inputs, you know that the neural network or system won't produce a specific type of output at all, or they could be probabilistic, where you can get a deterministic guarantee over a probabilistic property, such as saying we know for certain with 100% certainty that a neural network produces a specific output with 30% probability given its input comes from a specific distribution. Overall, our long-term goal is then to build a generalized framework for verified machine learning that can handle all of these applications. In the rest of this tutorial, I'm going to be focusing primarily on a subset of these dimensions, specifically on ReLU architectures, convex relaxations, abstract training, and look at deterministic guarantees. But this restriction can apply to multiple application domains and multiple types of specifications. So the first example of a specification that we can look at is inspired by the first types of attacks that were created. imagine you have a neural network that correctly classifies this image, I naught, as a car. We want to be able to specify that every image near to this image, with respect to how the original types of attacks work, classify to the same thing as this image. To do this, we take an L-infinity ball around this image, which specifies any image that is produced by modifying all of the pixels an imperceptible amount as measured by an L-infinity distance. This gives us essentially an interval or a box around the original image. In this case, our precondition is this box of radius 8 over 255, and our postcondition is that the network classifies every image in this box as a car. Now, you might say neural networks are actually operating on floating point operations, but we could potentially try to enumerate all possible images, but our precondition set contains 17 to the 3072 image, which is obviously infeasible if we want to enumerate all of them. Another possibly more modern type of specification that we might want to consider is robustness against geometric transformations. In this case, instead of perturbing each pixel uniformly, we take the entire image and we rotate it. And here, rotating an image isn't part of an L-infinity ball, because you could be permuting a few pixels by a lot, but because all of the pixels are changing together, the image still ends up imperceptible. So in this precondition, we specify all possible rotations of the image between -10 degrees and +10 degrees, and our postcondition is the same, that we classify every image in these possible rotations as a car. Another way of specifying these geometric perturbations is using generative models. This allows us to determine the specifications by learning them in much the same way we would learn a classifier. The state-of-the-art approaches to certification can be broken down into two main approaches: the exact methods and the incomplete methods. Exact methods aim to always output an answer, but which is nice if you need a counterexample or an answer all of the time, but because often they end up resorting to enumeration of something, there are scalability issues, and this isn't always possible. Incomplete methods trade precision for scalability and don't always output if a property is true, even if it is in fact true, but are always correct when they say that a property has been verified. So the key challenge in both of these is that to design scalable and precise automated verifiers. In part one, we're primarily going to focus on incomplete methods. So a complete verifier, in summary, is a program that takes a property, for example, robustness or fairness, and a program, for example, a neural network, and always eventually halts and says that this property is either proved or finds a counterexample. However, for general properties and general programs, this is undecidable. And even when you restrict it such that you're looking at specific properties such as L-infinity and W networks, this can be NP hard and thus very slow, and we might want, we need a faster system and we want to use approximations. An incomplete verification system similarly takes a property in a program, but isn't required to produce a counterexample. It's only required to say that it proved the property or it did not prove the property. This relaxation means that you could come up with an incredibly imprecise system that always says that it did not prove the property and it would be correct, but not particularly useful. Here we're going to focus on creating more useful systems. Most of these systems are built around the framework of abstract interpretation, which is a mathematical way of over-approximating program behaviors using transformations into programs that act on finite representations. It was invented by Patrick and Radia Cousseau, and it works by essentially taking a program F and computing a abstract version of the program G that we have an easier time computing and working with. And if we can show that the abstract program G satisfies our property, we will also know that our concrete program F will have satisfied the property. Abstract interpretation is particularly helpful in that it gives us a trade-off between precision and scalability, because there are a wider range of known domains and techniques that have been developed over the years inside of this framework. So at a high level, abstract interpretation works by breaking down the program into its fundamental operations. We can see what this might look like with a neural network. We start out with an approximation of all of the possible inputs that we want to verify. For example, with our car, we take the L infinity ball and we produce a representation of that in blue. After passing it through a layer and computing an approximation for that layer, we end up with an approximate or symbolic representation of the outputs at that layer that is always a superset of the concrete, the actual possible outputs given that input. If we do this for every layer, by the end of the program, we still end up with a correct, in that it is a superset output that corresponds to all possible ways that the network could behave for those inputs. So in order to build an abstract certification system, we need two parts. We need abstract shapes or domains. These are geometric shapes and representations of geometric shapes that are used to specify sets of possible program states. And then we need to design transformers for all of the different operations in our network or program. So the question that we have when designing formal verification systems is then, how do we formally define sound transformers? We can also ask if our transformers are exact or are they optimal. Abstract interpretation as a whole is concerned with questions such as what are we approximating? What are we approximating into? Whether our abstraction or the output of our certification is precise, how many false positives does it produce? Whether it's correct or sound, how we actually program and implement these representations, and whether the process of building these representations can be automated. So in more detail, abstract interpretation takes a concrete function or transformer F and produces an abstract transformer F sharp. What we want to do is we want to make sure that F sharp approximates F with respect to a concretization function gamma, which interprets a representation of a set of possible input values X. Here we say that I is the abstract element, is the representation of the set X. What we want is for F sharp to be sound for F, in other words, for the abstract transformer to be sound for the concrete transformer, in that applying the transformer F sharp to an abstract element and obtaining the set of concrete values corresponding to the result must include more points then first concretizing the abstract element and then applying the concrete function. We can also ask whether a transformation or transformer is exact. And this is interesting because abstract interpretation can include complete analysis. We say that it's exact similarly to before by relating the concrete and the abstract transformers. Specifically, we say it's exact if applying the transformer F# exact on the abstract element I and then obtaining the set of concrete values corresponding to the result produces the exact same set of points as first concretizing the abstract element and then applying the concrete function. So the domain that we're specifically going to use for the rest of part 1 and examine for the rest of part 1 is the box domain. This is essentially a set of intervals. It's represented by a lower bound and upper bound for each variable in the program that is being analyzed. Typically, you start out with -infinity and infinity for everything but the input variables of the program. And it's a useful specification, or it's a useful domain to look at because while it does not keep around relations, it's fairly easy to program and analyze. And the transformers, as we will see, are also continuous and have nice properties that are easy to define. So to create transformers for the box domain, we're essentially applying interval arithmetic to each of the lowest level operations in a neural network. While a neural network contains batch matrix multiply, affine operations, and ReLUs on many neurons at the same time, we can analyze and define our transformers in terms of these very primitive operations, which is easy to analyze theoretically and fairly easy to implement. Furthermore, it's not a far step to take these and batch them in the way that a neural network does so that we can perform the sort of computation on a GPU. If you're unfamiliar, ReLU of a scalar value is just the max of 0 and that scalar value. And the sharp here denotes the abstract version of the operation. So the most counterintuitive thing about abstract interpretation and the box transformer in particular is that it is not exact. We can see this just by looking at matrix multiplication of an input x1 and x2 to an output x3 and x4. Suppose that the inputs of x1 ranges from 0 to 0.3 and input to x2 ranges from 0.1 to 0.4. We then compute x3 as the sum of x1 and x2. We compute x4 as the sum of x1 minus x2. And using interval arithmetic as defined on the previous slide, we would get that the outputs of x3 ranged from 0.1 to 0.7, and the output of x4 ranged from -0.4 to 0.2. Now, of course, if we don't relate these two terms, we're going to include points that aren't actually possible, values for x3 and x4 that cannot be represented. For example, there is no combination of x1 and x2 in the ranges here that would produce x3 equals 0.1 and x4 equals -0.4. We can visualize this here where the output box is in bright orange and is a clear strict superset of the actual possible values, which is the diamond in the center. So the key point is that the box transformer for affine and ReLU computation may not be exact. It ignores the relationships between the neurons. Nonetheless, it may be enough to verify properties of interest. So we're going to see in detail by looking experimentally if it's enough to verify properties of interest. First, though, let's look and see a case where Box does in fact succeed at verifying a property. So imagine, like before, we have two pixels that range from 0 to 0.3 and from 0.1 to 0.4. And now we pass them through a full neural network. And we want to see that the neural network is always classifying inputs in these ranges to 0. Specifically, that the output O0 is greater than the output O1. So we can walk through this, and we see first that x1 and x2 are assigned the intervals 0 and 0.3, and x2 is assigned 0.1 and 0.4. x3 is computed by adding x1 and x2, so we get the interval 0.1 to 0.7. X4 is computed by subtracting x2 from x1, so we get negative 0.4 to 0.2. We can then compute the ReLU, which for x3 is simple since it's never negative. We just get 0.1 to 0.7 again. For x6, we have to cut off the part where it was negative, so now it ranges from 0 to 0.2. Finally, we compute the output O0 as the sum of x5 and x6. And we just add the lower bounds and we add the upper bounds together to get 0.6 and 1.4, and this is incorrect. I think there's a number missing there. But for O1, we would multiply 2 by 0.1 and 0.7 and then subtract negative 0.2. And this is not that value, but anyway, imagine that this did actually produce the values 0.6 and 1.4 and negative 1 and 0.4. And in this case, we would be able to prove the property because the upper bound of 0 of O output 1 is 0.4 and the lower bound of output 0 is 0.6. And thus output 0 is clearly greater than output 1. If we were to increase the ranges of the pixels slightly so that x1 ranges from 0 to 0.6 and x2 ranges from 0.1 to 0.7, we will see that the network no longer correctly or provably verifies that output 0 is the correct output. So we can walk through again. X3 is now the sum of x2 and x1, which is 0.1 to 1.3. X4 is x1 minus x2, which is negative 0.7 to 0.5. Taking the ReLU of x3 again gives us the same result, 0.1 to 1.3. Taking the ReLU of x4 again caps everything below 0, so now it's 0 to 0.5. And here we add it together and again produce this not quite correct result, 0.6 to 2.3, and this other not quite correct result, negative 1.3 to 1.6. And then using box, we would have failed if we imagine this is the output that we actually have using box. We would have failed to prove that the network classifies the inputs correctly for any input there because the output 1 has a maximum value of 1.6 and output 0 has a minimum value of 0.6, so they overlap. So then we can ask whether box is precise enough for common properties on actual data sets. And we can see this by training a data set, or training a network, a convolutional big network on fashion MNIST, and testing it on robustness perturbations, L-infinity robustness perturbations with radius 0.1. With standard training, we can see that PGD, which is a common attack, is able to attack the network well and cause the network to only have 52% accuracy. So we can't certify anything with box there, which is reasonable because it might be the case that none of the images in the data set are actually robust for that network. Just because PGD wasn't able to find an attack in 50% of the cases doesn't mean there wasn't a stronger attack. However, when we train with PGD, we find that the PGD adversarial accuracy goes up to 97%, which is really good. And it's pretty commonly accepted that PGD is in fact a quite strong defense technique for training, and it is likely that the network is actually robust. But in this case, we cannot certify that it's robust. We expect that a number of images should be actually certifiably robust, but we cannot do it with box. So box is not precise enough for real used networks. So we have two options. The first is that we can use a more precise verification or complete verification, and we'll discuss that more in part 2. And the second option is that we can train nets such that they can be used for verification with, for example, box. So the key idea with training for verification is that we want to be able to use abstract interpretation inside of the training loop. So given a spec S, some training data D, and a loss L, we want to find weights for a network that minimize the number of inputs that can't be certified. Now, this sounds very similar to the standard training goal, where we don't care about certification, because there we're given a spec training data and a loss, and we want to find weights that minimize the number of inputs that are incorrect with our very simple input and output spec. This can be formalized in this equation to the right. We want the argmin of the weight sets theta that give us the lowest expected loss over worst possible inputs from an abstract output, an abstract element that is the output of the spec of the network. It's important to recall here that box transformers are continuous and mostly differentiable. We can look at the addition transformer for interval and see that applied to two intervals A to B and C to D, we just add the first part, we add the lower bounds and we add the upper bounds. So addition turns into two addition operations. Similarly, ReLU turns into two ReLU operations. We know that we can optimize addition well with gradient descent, and we know that we can optimize ReLU well with gradient descent. So it follows that we should be able to optimize the abstract addition and abstract ReLU fairly well with gradient descent. So the pipeline for differentiable abstract interpretation, where we use abstract interpretation during training, is we first create a precondition over the network inputs. Phi again, we pass it to a network n parameterized over its weight set theta, and then we compute an abstract loss on the abstract output of the network on the precondition, and we take its upper bound and we ensure that, and we optimize for its upper bounds decreasing. And then we backpropagate through the entire abstract computation and abstract network to update theta. In other words, we're using automatic differentiation, for example, a system like PyTorch, over the verification program that produces a single value upper bound on the highest possible loss over spec. So we can see if this actually improves our ability to certify networks. And when we train with DiffAI, we get up to 95.8% adversarial accuracy on PGD, which is expected since this is a harder training problem than just PGD training. And now we're able to certify using Box. We can certify 87.2% of the training set, of the test set. However, these systems since DiffAI have not been improving significantly. The state of the art has plateaued pretty far from what we would need to use certified defenses in practice. One of the best results gets at most 60.5% certified robustness on CFAR 10 with a radius of 2 out of 255, which is a fairly small radius. Whereas standard training gives greater than 95% accuracy for CFAR 10. And this is a hard hit to stomach if you're using neural networks industrially. A 30% decrease in accuracy is quite meaningful. So this raises some fundamental questions. In particular, we have universal approximation for standard neural networks, which means that given any function and any approximation tolerance, we're able to theoretically construct a neural network that approximates that function. And this implies that robust neural networks also exist that approximate robust data sets. But as we saw before, Box might not be able to prove a property that is in fact true. So this isn't enough. We need to be able to produce networks that are robust and provably robust. Now we know neural network verification is NP hard in general, so it's not really good enough just to say that we can prove that it's robust with SMT, because for CFAR 10, you might not be able to use SMT to create a network that gets 95% accuracy there. So we want robust and efficiently certifiable networks. As it turns out, we have two possible answers to this question. We can create networks that are universal approximators and are certifiably robust with interval. But there are limits to this on the shape of the network and the types of certification, which we found in the next paper, the fundamental limits of interval arithmetic for neural networks. So now I'm going to explain how this is possible in more detail. So the easiest way to see how this is possible is to look at a simple construction problem, which is just whether we can interpolate data, or specifically whether we can classify a finite data set completely correctly. So imagine even in one dimension, we're given points, a finite number of points, k points, x1 through xk, and positive or negative labels for these points, l1 through lk, and a certification radius, epsilon. We want to know whether there is a network n such that it classifies these points correctly and provably robustly using interval analysis. And we want to do this for any smaller radius than epsilon. So this is possible, provided that the epsilon we're using is smaller than half of the distance between the closest 2 points in the data set. So we can do this by constructing a neural network from a sum of bump functions or indicator functions, where each of these functions is designed to approximate, or it's designed to tell you whether the input or the interval around the input is within a specific range epsilon. That we add these bump functions together weighted on the labels that are used, so that we use a positive bump function for a positive label and a negative bump function for a negative label. The width of these bump functions is designed so that 2 points never have activated bump functions that overlap. Then we want to be able to show that if we are to provide an interval and do interval analysis on a bump function around a point with a radius smaller than epsilon, the output interval has 0 width, and thus we can prove our final property. So we can build the bump function easily as seen here. We start out with 2 upside down ReLUs so that, and I wish I could use my mouse, and I'm sorry that I can't, so that it looks essentially like an infinite mountain on either side. The width of the plateau of the mountain would be of size epsilon, and the slope of the sides of the mountain would be inverse d. And we raise it so that it is the plateau happens at 1. We then cap off the mountain so that we have this hat-shaped bump function, and we can cap the error from the intervals given outside the plateau. So we want to verify that this bump function has 2 properties. The first of these properties is that for all epsilon prime smaller than epsilon, if we give the bump function an interval of size epsilon prime around 0, its lower bound is still going to be greater than 0. So we would have been able to prove our property. So we can see this using a sanity check on a simple bump function instead of proving it in detail here. Suppose we start with a bump function of width epsilon and tolerance, or width 1 and tolerance 1, and we give it the interval -1 to 1. And this is, of course, the full width interval. We can then compute it by plugging in this interval into the equation seen above. And it's fairly simple to go in and apply interval arithmetic in your head using the operations that we saw before, because they are mostly just applications of known operations to the lower bound and upper bound individually. So we do that here, and we get ReLU of 1 minus ReLU of the interval from -1 to 1 minus 1 minus ReLU of the interval of -2 to 0, which we can simplify again. Here, when we subtract 1 from the interval -1 to 1, we get -2 to 0, and ReLU of -2 to 0 is just 0 to 0. We can ignore 0 to 0, and we get ReLU of 0 to 0, or we get from ReLU of -2 to 0 the interval 0 to 0 again. So finally, we have ReLU of 1, which results in the interval 1 to 1, which is clearly greater than 0. The second property that we want to check is that the bump function outside of this plateau also produces intervals of 0 width that we can prove things with, singleton intervals, and says that the bump function isn't activated on those. So again, we can do a sanity check and plug in the interval 3 to 5 on this bump function. We can see this interval visualized in green over the example figure to the right. It's now outside of the upper plateau. And plugging in, we get this value shown here. And we can simplify by negating -3, 5 and subtracting 1 to get -4 and to -2. And for the other ReLU, we get the interval 2 to 4. And simplifying again, we get 1 minus 0 to 0 minus the interval from 2 to 4, which of course simplifies to 0, 0. So our sanity check has passed. Once we have these bump functions, we add them together, and knowing that they don't overlap, we never have intervals that have any width added to any other intervals, or intervals of different width added to other intervals at points around epsilon around each of the data points in our data set. Of course, this doesn't cover the cases that we were discussing before of universal approximation, but it can be generalized to cover these cases. So for universal approximation setting, we're given an input function f from a box to a real numbers and a tolerance delta, and we ask, is there a ReLU net n that is box provable delta approximation of f? And specifically what this means is that for all L infinity balls, we have the neural network applied to that ball being a subset of the expanded concrete output of the neural network on that ball. And it turns out that we can do this. We came up with the universal approximation with certified networks, specifically the interval certifiable universal approximation theorem. And this is based on the previous construction, essentially, but generalized to networks with different possible outputs than -1 and 1. The insight here is that whereas traditional universal approximation partitions the input domain indirectly on delta, interval universal approximation partitions the output range directly based on delta, creating slices of these bump functions. This is akin to the difference between Riemann integration and Lebesgue integration. The second insight is that whereas our bump functions before only worked for a small range of epsilons, to get it to work for the full range of interval widths, we need to use a bump function for each rectangular grid subset, minimally containing a box that is fully active in the slice. Of course, now we're talking about a network that is the size of a power set of a grid on the input and output domains, and this is not feasible. So we're still left with some questions about whether it's actually possible to train certifiable neural networks. And in fact, the interval certifiable result contradicts the gap that we see in reality. So in order to explain this gap that we see in reality, we need to look at our restrictions again and ask if they made the most sense and if they are the complete story. So before we required epsilon to be smaller than half of the distance between the closest 2 points, now we can drop that restriction and possibly look at other restrictions. So one restriction that's interesting is, what if we're only using one-layer networks? Traditional universal approximation works even if you just have one-layer networks. It turns out that you cannot have interval certifiable approximation or classification with only one-layer networks. And to see this, we can pick a data set intentionally. We can construct a data set where you cannot classify that data set certifiably. The data set just has its points equally distributed and switches between negative and positive classifications. The size of the data set depends on the size of the epsilon that you want to use, but in general, we show that for any radius epsilon, there is a data set that no one-layer neural network can provably classify. Of course, in practice, neural networks are not one layer, and the gap that we have seen in training still applies when using deeper neural networks. So we have a stronger result that applies to any neural network of any shape based on ReLUs, that if the data set that the network is trying to classify contains 3 points that are equidistant and separated by the radius epsilon that you're trying to use, for certification. And if the outer 2 points are one label distinct from the center point, then there's also no such network that can provably classify it as per this notion of provably classify. The proof here is by structural induction on the shape of the network, generalizing to the observation that precision is always lost when the network needs to approximate or classify something not invertible. And both of these theorems are in the paper, The Fundamental Limits of Interval Arithmetic for a Neural Network, which we just released on arXiv and are submitting now. However, this story is not yet complete. There still remain fundamental questions about why training does not work, why we have not yet closed the gap between certifiable training and standard training. These limitations apply to pretty restrictive scenarios, for example, that you're only using ReLUs, that you're only using box abstractions, and that you're only building transformers for the most primitive of operations. The second you leave these restrictions, these theorems don't necessarily imply, but we still don't have good techniques to train. So in summary, we've introduced the concepts of complete and incomplete sound methods for neural network certification. We defined the box convex relaxation and its best transformers, an instance of an incomplete method. We demonstrated how to train with box to build models that are amenable to certification. And we demonstrated the basis for the theoretical analysis of training models. And thank you. Are there any questions? There are. Sorry, I couldn't switch back to the questions while presenting.
Thank you, Matthew, for your wonderful talk. If you have questions, you can raise your hand.
Thank you. Yeah, awesome talk. Said it's an awesome. The whole line of work is amazing. I do always have this niggling worry about using the term provably robust or verified neural network when it comes to these robustness properties, just because. Let's say you verify that your neural network is driving a self-driving car and is recognizing images on the road is robust. What you've verified is that it's robust around the images in your training data set. And yes, you've classified it's robust over an infinite set of images, which is super cool. But the chances of your neural network ever encountering one of those images that you have verified over in the real world is still almost zero, right?
Yes. So, Art, while you can stop the question of verification at does it certify all of the images in your test set, you can also use these certification systems if they are efficient enough at runtime and make decisions based on whether you were able to certify network or images that you've seen in the field. So you might, in a self-driving car, only use the decisions that you were able to certify were correct.
But you've managed to certify ahead of time or at runtime?
Both. So certifying ahead of time gives you a guarantee essentially on your ability to certify things correct at runtime, but it's a fairly weak guarantee. It's true. Certifying at runtime is a strong guarantee that says this image that this decision that I have made is decidedly robust.
Okay. Yeah, that makes sense. Cheers. Thank you.
We have another question.
So in Bayesian machine learning, we often keep track of not only our prediction, but also the uncertainty of each component of our prediction to try to build a probability distribution. So I'm curious, is there an interesting way in which certification and Bayesian methods can kind of interact? Like maybe, for example, showing some probability bound that, like, rather than say, so perhaps, something would be certified if it has a 1.0 probability or a probability above, so on and so forth. But I don't know, I guess, yeah, are there any interesting interactions between...
Oh, sorry, you cut out.
Oh, sorry. Are there any interesting interactions between a certification of robustness and neural networks which also report their uncertainty? And in particular, can we get it to the point where rather than, either having a certain prediction or no prediction, we have a prediction and it tells us how certain it is and have some kind of mapping between how certain it is and epsilon, for example? So that, like, if we have certainty 0.5, then epsilon's got to be at least this small, though it could potentially be better.
Sure. So in the second part of our talk, I think Geigendeep is going to mention a little bit more about probabilistic or verifying probabilistic properties. And that leads into what you said. If we can verify probabilistic properties online, then you can have guarantees about your probabilistic statements. I haven't seen anything that uses probabilistic verification like that, but it is certainly feasible or possible.
Is there any other question from ALMeet? No?
There's one here.
Okay. Oh, there's one.
So how do my methods extend to multi-class neural networks? Is it just a dimensionality issue, or is something fundamentally different about scaling these? In fact, multi-class neural networks are mostly the same as single-class neural networks. The biggest issue there is that most multi-class neural networks are trained using softmax, but you don't typically use softmax during test time. During test time, you just take the output linear layer and apply and use that directly and take the maximum output of a range. So for box, because it's not relational, it's really hard to get multi-class working. But as we saw in the slides, FMNIST is multi-class. It, I think, has 10 classes. And Box is still able to certify 87.2% of these images.
One more question about this slide. Is this the percentage of images that are certifiable, so 87.2, is that from the test training split? So is that just the test percentage?
That is from the test set.
That's from the test set. Okay.
Yeah.
Okay, I think that's it. Let's thanks Matthew for his wonderful talk.